Okay, so now we can start. We have 108 people now. So I'll just start my presentation, and after my presentation, my team members, Evan Fernandez is there, Paris Palkar is there, and Manjil Situla is there with me today. So Paris, you can just wave. Evan also, you can just wave your hands there so that they know you.
Yes, ma'am.
Okay, fine. So I am Payal Mukherjee. I am working as a senior project manager at FOSSEE IIT Bombay. And Evan, Paris and Manzil, they actually take care of the technical part of the CFD vertical of FOSSEE. Okay, so now I would request all of you to please switch off your cameras, because then we will get a better bandwidth. So let me start with the presentation for today. ये close करेंगे. Okay, so am is my screen visible?
Yes, ma'am.
Okay, fine. So one more time, a warm welcome to all of you, and a very good evening and namaste from FOSSEE IIT Bombay. So today we are here to know about FOSSEE, what we do in FOSSEE, what we have to offer you from FOSSEE IIT Bombay, and we will get ourselves introduced to OpenFOAM, which is a toolbox, which is a free and open source software for the CFD people, the people who are working with CFD, for the CFD enthusiasts, for the learners and teachers of CFD. So we have a lot of information to give it to you. That is why we have invited all of you here today. So let me move ahead. So these are the things that we are going to cover in today's orientation session. So this 2 hours is very important because today we will talk about the OpenFOAM's capabilities, how as students and as teachers you can start learning OpenFOAM, how you can gain expertise, and how you can apply your knowledge to solve CFD problems as a researcher, as a student, as a say undergraduate or postgraduate student, as a teacher, and as well as CFD professionals who use CFD in your corporate lives. And I'll also let you know how we work with students and teachers so that they can publish their research work and their just mini projects in the CFD website of FOSSEE. So let me begin with what is FOSSEE and who we are and what we do. So FOSSEE is a project which has been developed at IIT Bombay, and it is funded by the Ministry of Education, Government of India, and this project was launched way back in the year of 2009, and we are still here existing because FOSSEE is about nation building and skill development of students. So when I talk about students, the students are learners at present, but after a few years they are going to join either academics or they will be joining corporate. The corporates can be MNCs, it can be MSMEs, or the students can also become entrepreneurs and they can launch their own startups. So FOSSEE is for all of you. It's for the students, it's for the teachers, it's for the corporate people. So that is why FOSSEE is actually contributing to nation building, wherein we are encouraging the people to become independent in terms of the knowledge of the software, so that you can use the software in your own fields and excel. So FOSSEE actually stands for Free and Open Source Software for Education, and why the double E here is when it was launched in the year of 2009, it was only focused on the engineering education stream, but now FOSSEE is open to other fields as well. For example, we have GIS, we have animation, we have some statistics tools. So it is not only limited to the engineering field students now. That is why we call it as free and open source software for education. So that was about FOSSEE, the background. And what we do in FOSSEE is primarily our focus is on training. That's how we build the knowledge base of students and teachers and the corporate people. And we also develop a few FOSS. For example, eSIM is a software that we have developed at FOSSEE. We are also developing the GUI for OpenFOAM. So these are some of the development works that we are doing, but our main focus is reaching out to people and training them. and that is how we are a part of the NME ICT, which is the National Mission on Education through ICT. And our mandate is to reach out to each and every corner, each and every vertical, each and every financial vertical, and each and every location of India, so that we can uplift the knowledge base of the students. There are some remote places of India where the students are not exposed to primary institutions, tier 1 level institutions, and in some of the cases financial restrictions are also there for some of the students. So that is why we are here. We are here to help the students, and this is the one of a kind project that is being promoted by only one government in this world, which is the government of India, because no other government promotes the usage and learning of free and open source software. So we are really thankful to the government of India and the Ministry of Education for promoting FOSSEE. And FOSSEE, actually the training is skill based. That means we are not very much focused on the theory part of the knowledge. We are more focused on the practical aspect of the free and open source software or whatever tool that we are teaching to the students. And this training is mainly through internships, fellowships, workshops, hackathons, competitions, and also some of the courses. For example, we have a course for CFD, for eSIM also we have a course. This we have launched very recently, and I'll talk about it in details in the next few minutes. So FOSSEE is actually uplifting the education, as I just spoke, and it actually benefits your higher education and employment potential. So that's what I mentioned a while ago, that today you are students, tomorrow you can actually be interested in the academia, so that you can so for that you will have to apply for higher education, and FOSSEE will support you in a big way in this. And we promote all this education and all these trainings and through FOSS. So let me now talk about why we are insisting on the knowledge of FOSS. Why not any other proprietary software? So the first and most important advantage of using FOSS is its cost effectiveness, because we can all use FOSS legally and free of cost, because it comes under the licenses of GPL and BSD, so that we are free to use it without incurring single rupee. That is why it is the most important feature of FOSS, and that if you are saving, say, lakhs of rupees, if an institution is saving a lakhs of rupees, if a corporate is saving a lakhs of rupees, that money can be diverted to some other educational or some other resourceful expenses, some other developmental activities can be done. So cost effectiveness is one aspect. The other three aspects are its code modification. You can modify the code of the free and open source software, you can distribute it, and you can also distribute the modified version of the codes. So these are the four aspects that makes FOSS very much effective for use. You don't have to incur any cost to use it or to learn it, because FOSSEE is giving the training on FOSS completely free of cost. Okay, and we actually this CFD vertical of FOSSEE, we have a group of people whom we call faculty partners, and we have a group of people from the CFD industry whom we call the advisory board members. So here there is a constant exchange of knowledge that is actually promoted by FOSSEE, and it is very important for any country, for any economy to develop, if we have a constant exchange of knowledge between the academia and the industry, and FOSSEE promotes that. Now let me talk about the training portion in detail. Okay, so we have internships, fellowships. Internships we actually float twice a year, in the beginning of the year, and we will be announcing it in the month of August again for the autumn semester. So it is completely online. It's the duration is 3 months, and for the fellowship it is only for the summer months when the students are free, and we float it or we offer it in a hybrid mode, so that the students can come here at IIT Bombay, they can stay here at IIT Bombay, and they can work. Okay, and workshops we announce ad hoc. I hope in the next workshop when we announce, we will get all of you and we can learn together. We also offer faculty development program for all the faculty members once a year, preferably during the summer. We have some year-long projects. For example, in the CFD vertical, we have case study project, research migration project, lab migration project. I'll talk about all these later on. So these are all year-long projects. These are apart from the internships and fellowships. Like, we don't have any limitation of duration to participate in these projects. Okay, and we also conduct the learning program on CFD for the OpenFOAM vertical. So all these learnings actually will enable students and faculty members to publish their mini projects, paper, conference papers, and journal papers, book chapters, and so on. So this was about the training that we offer. And what are the benefits from the training? Number one benefit is the experience or the training by itself, because it is very enriching for the students. And we publish all your projects at fossee.in, cfd.fossee.in. I'll just show you the repository that we have towards the end of this program today. We award certificates, okay, and there is an opportunity to work with the FOSSEE team of IIT Bombay. We have 5 members, and this team is led by Professor Chandan Bose, who is our mentor of this team. So there is an opportunity to work with the team. And for the students who are joining us as interns and fellows, there is an opportunity to work with the faculty partners. We have faculty partners from all over India and abroad. Some faculty are also from IIT Bombay. So it's an excellent opportunity that FOSSEE gives you to expose yourselves and gain experience from the faculty who are working as or who are as a part of our team as faculty partners. And there are also people from the CFD industry who guide the interns and fellows along with the faculty partners. So in this way, they are actually getting they are introduced to the problems that are dealt with the CFD industry at present. It is very important, because if the students are exposed to the the real time, the real life problems that the industry is dealing with at present, they are actually preparing themselves for the job industry. Okay, so now on the screen you can see a lot of tiles, a lot of icons, and some names. So these are all the logos for the FOSS, for the free and open source software that comes under the FOSSEE umbrella. So we train Scilab, we train OSDAC. So all these things, just like OpenFOAM, we have training and learning opportunities for all these FOSS. Okay, and I would like to say that the people who are from chemical engineering department should also learn DWSIM and OpenModelica along with OpenFOAM. That will be a very helpful thing for you. So we have Scilab, we have Python for the engineering people. I just talked about the QGIS part. FLOSS Arduino is for the open source hardware. Focal is for the people who are interested in animation. Okay. So now let me talk about the mapping part. We also have Koha that was not listed in the tiles that I showed you. Library management system is very important for all the institutes. I need not mention this. So you can also have the opportunity to implement Koha in your libraries. For CSIT you have Python. So you can just go through all this, and you will get to know what we have, what FOSSEE has to offer for all the streams of education. And this table shows the mapping, wherein you can see one FOSS against very famous proprietary software. For example, MATLAB is a very famous proprietary software, and we have Scilab for it. So we encourage you to use FOSS wherever possible. So in some specific cases, you might need to access the proprietary software, but most of the time the FOSS actually has all the capabilities that a proprietary software has. So, and in some cases actually open source softwares are much better as compared to the proprietary software. Actually the proprietary software might have more developed GUIs, and they might be much more user friendly. But in some cases, for example OpenFOAM is actually, in some respects, it's better than ANSYS Fluent, because for the researchers who use research and customization, OpenFOAM is much better, because the source code of OpenFOAM is free, and that is why for the creation and modification of solvers and models, OpenFOAM is much more effective as compared to ANSYS Fluent, because ANSYS Fluent is considered as a black box, just drag and drop things. So it is sometimes for the researchers and for high level users, OpenFOAM is a better choice. And also it is easier to implement in some models, for example multi-phase turbulence and combustion model, where you will find OpenFOAM is much more effective as compared to ANSYS Fluent. So my colleague Ivan will actually elaborate on this when it comes to his session. So here we have more. So FreeCAD for AutoCAD and DWSim for Aspen Plus, OSDAG. So if needed, I can share this table with you later after this program. So now let me talk about how can the faculty members get involved with us and contribute. So I would request each and every faculty member who has joined today to please guide at least one student from your institute so that they can submit a case study project. Okay, so what is a case study project? Now let me come to this. So we call cases as small problems in CFD. So the student is free to choose any topic of their choice, of their interest, of their background, and form a problem. And thus the faculty members are expected to help the students to form a problem on which they can work. Okay, and then the student will apply the knowledge of OpenFOAM to compile it and present a case study project. So in this session we will talk about the case study project also, how to compile, how to submit, what are the guidelines, everything my team members will explain in detail. So you can also submit a research migration project. So research migration projects are actually very much effective and useful for the research scholars. So it is in this research migration project, we are expecting that you will refer to any research problem which is published in a renowned journal and just replicate the problems using OpenFOAM and prepare a report and submit it as a research migration project. Lab migration project is actually when we are assisting the colleges, the institutes, to migrate their labs into OpenFOAM from any proprietary software to OpenFOAM. So we work with the faculty members propose their lab topics, the experiments, and we help them to solve it using OpenFOAM, and that's how the lab is migrated. So faculty members, if you are really wanting us to help you to migrate your lab to OpenFOAM, please write to us and we will share the exact steps with you. Okay, you can also arrange an orientation session at your institute on FOSSEE. And so that orientation will not be only limited to CFD and OpenFOAM. We would like you to apply to us so that we can help you to arrange an orientation session at your institutes on FOSSEE. Okay, so we will in that orientation session we will talk about FLOSS Arduino, we will talk about eSIM, we will talk about DWSIM, Scilab, Python, everything. So that's how you will get more knowledge on what all we have and how can you get involved with us. That will benefit you. And this orientation session, this involvement of FOSSEE will actually be beneficial for each and every faculty of your institute and your institute as a whole, because then this actually will add on to the ranking of the institutes. Fine. So we can talk about this later on. You can write to us and I'll get back to you. And recently we have also introduced a course on OpenFOAM. This is a 1 semester long course, and we have already offered this course to VIT Vellore, and in this semester many more such institutes have applied to us and will be beginning in the month of August. And this is an online course. Basically we cover the practical aspects of OpenFOAM in this course, and this course can be incorporated in your regular course curriculum, which is actually recommended by us and you can also incorporate these courses as a value added course. In many of the institutes it's very difficult to put it in the course curriculum because there are a lot of paperwork and all, but then to start, if you want to start it immediately for the next semester, I mean for the 2027 semester, the spring semester, we can work together and we can actually come up with the schedule and we can get started as a part of the value added course. Okay, so I just explained what is case study project. So these things are all open throughout the year. Like I mentioned that internships and fellowships are for a certain duration, but the case study, research migration projects, are open throughout the year. You can connect to us, you can start learning OpenFOAM, and you can compile a case and submit. So that will be your first step towards the learning program of OpenFOAM. Okay, yes, and let me just share about the OpenFOAM learning program. So this thing we do twice a year. So basically we get a lot of applications for the internships and fellowships, but we have a limited seat for these programs, and we cannot accommodate everybody. But we see that many students have that potential, have that interest to learn, and we shortlist them and we invite them to join the OpenFOAM learning program. In spite of that, we have a form. I'll show you the website how you can apply. We have a form in which you can enter your name. You can register yourselves for the OpenFOAM learning program, so that when we float this program again around the month of September, you can all come to us and we can learn together. So this was from my side. So just note the contact ID and our website. I'll show you our website towards the end of this program once again. So that was all from my side. Now I'll request Ivan to please take over and start the session. Yes, please go.
Thank you, ma'am.
Yeah, thanks.
Should I present?
Just wait for a second.
Okay.
Okay, Ivan, yes, we are done. We can start.
Okay, ma'am. Yeah, is my screen visible?
Yes.
Okay. And can someone confirm now also whether the full screen is visible?
Yes.
Yes.
And the slides are changing, right?
Yes.
Okay. Okay. Thank you, please. Yeah. So good evening, everyone. And I am Evan Fernandez. I'm a research assistant with FOSSEE IIT Bombay. And welcome again to the orientation program for OpenFOAM and CFD. So as Payal ma'am was asking everyone over here whether you have done CFD or do you know what exactly CFD, and a few of you have not yet done it, so it's fine. We'll begin from the basics for now, and we'll explain what exactly is CFD and what exactly is OpenFOAM as well, and how can you start with it. Now, so the first question is, what is CFD? For those of you who know it, it's obviously computational fluid dynamics. But for those of you who don't know, it's a method. So in this, you have numerical methods, and using computer algorithms, you solve this in an iterative process to analyze fluid flow. Now, these fluid flows can be simple fluid flows, or they can be heat transfer flows. They can also be multi-phase flows as well. To better explain this from a graphical point of view, so in this case, let's switch to this one. Okay, so this is a simple cube. In this, you have your physical parameters and all the forces acting on the cube. So in this case, you have it in the X, Y, and Z direction. So you have this volume, and within this, you have some forces that are behaving on it. Now, these are all your physical terms. This is what we as humans are understanding and what we can solve on a piece of paper or through some computer algorithms. But in yes, as humans, we are able to understand because we've learned it. But if you simply just put this equation into a computer, it will not understand what you're trying to do. So this is where your numerical algorithms come into play. So all of these equations, it breaks it down into simple linear algebra. That is what a computer will understand, and using time, and it will derive time. It will using derivatives, it will derive your time, and it will solve these linear algebra equations for these equations, and then you get your output. So in simple terms, you have physical equations using computer algorithms. You place it into a computer algorithm. Can anyone else just confirm whether it's am I audible or am I not audible?
Yes, people are raising their thumbs. So
okay, fine. Yeah. So at this point, you get the idea, right? So you have these equations, you put it into a computer, and then you get the simulated output. Now, in this case, the simulated output is for compressible flow, and this is a shock wave over a hypersonic vehicle. Okay. Now, when it comes to domains in CFD, there are quite a few. These are just listed. These are the most common ones. So you have incompressible flow. Then you also have compressible flow, the one that you just saw. Along with that, you will also have heat transfer. Now, heat transfer can be done separately, or it can be coupled with incompressible flow as well. Same with multi-phase. So you have multi-phase, it can be coupled with heat transfer as well. You also have combustion. So in OpenFOAM, you can do combustion. In CFD also, you can do combustion. And the second line that you see over here, these are a little bit different. So when it comes to fluid solid interaction and computational aeroacoustics, these are some things that you may have to couple with a CFD solver. So by default, there are a few softwares that do this by default, but most of the softwares you will have to either combine or you'll have to compile the solver itself and then couple it with your CFD solver, or you can run these independently and then post process them separately. And lastly, you have multi-physics problems. So these can be a combination of, say, incompressible flow with fluid-solid interaction, or acoustics with multi-phase, or with heat transfer. So those are the cases which are far more complex, and you may have to either couple a solver, and in this case, you may also have to write your own code and create your own solvers. So these are a little bit advanced. These are intermediate, and these are the most simplest ones to understand. Now coming to the application sector. So now we've told you that there is CFD, there's a software named OpenFOAM, there are other softwares as well, but where exactly is this being used? So if you just take CFD, like computational fluid dynamics as a whole, these are a few areas where it is widely used. Okay, so now in the automotive and aerospace industry, you will find them for design optimization. Whereas in power generation, so say you have nuclear power and nuclear reactors, in that if you want to find out how much liquid or how much water you will require to cool down a particular part of that reactor, you can do simulations as that as well. In hydraulics, if you have a certain weight you want to lift up and how much pressure will be required for that fluid to be lifting that particular weight, that can be done in hydraulics. Same for environmental sciences and biomedical. In biomedical, it's of lately being it's widely being used in biomedical. So recent studies were being done using CFD and aeroacoustics. In this case, they were trying to find the blockages in an artery in your heart using sound waves. So that can be done using CFD. So those are again a bit complex to begin with, but again, these are some of the options that are still available. In sports also, you can use these applications, and widely in HVAC for cooling and ventilation. Now, these are a few practical examples that are done all in OpenFOAM. So this is a simple flow over a cylinder, flow over an oscillating cylinder. This is a simulation of a flow over an F1 car. And this is a multi-phase simulation for flow over a ship hull. This is an airfoil, and this is an air horn in which you can see that the sound wave is being propagated outward while this object is moving. And this is a combustion simulation. So all of these can be done in OpenFOAM. It all can be done in any other software as well. Now, to name a few of the software, so if you just simply type on Google CFD softwares, you will find these are the most famous ones you can see. So you have ANSYS, as Payal ma'am said, that you have ANSYS, and this is the commercial variant, and this is the free and open source variant, that is OpenFOAM. And for multi-phase or multi-physics simulations, you can also use STAR CCM, COMSOL. And over here, if you see SU2, that is Stanford University code. So this is developed by Stanford University. SU2 and CodeSaturn are two of the other free softwares that you can use. But again, now each of these are good in their own fields. But when it comes to coupling most of the applications into just one software, that is where ANSYS and OpenFOAM come into play. So if you want to do multi-phase simulations, you can do that in ANSYS and OpenFOAM. If you want to do heat transfer simulations, you can do that in these two as well. You want to do simple flow simulations, again, you can do it in this. So you can say that ANSYS and OpenFOAM are like a jack of all trades, but they also have their own capabilities and their own limitations. So now if you simply take ANSYS and OpenFOAM, now ANSYS, as Payal said, that you have a subscription fee that you have to pay. Now, since all of you are students and for professors, it's paid by the institute. So the institute bears the cost of taking a subscription for ANSYS or for these commercial softwares. But when you graduate, and if you want to start your own startup later on in life, you may have to pay a high subscription fee. So these subscription fees run in lakhs. So just to take the basic version of ANSYS, you would have to pay around 30 lakhs to begin. And again, this is just for the base variant. Now, say you want to run it in an HPC facility. Again, to scale this up, you will have to again pay the cost for each and every node that you buy. Along with that, you'll have to pay for the software to apply it in that particular node. Whereas now this was in terms of buying it. And the second thing was in terms of scalability. Now, this is where OpenFOAM may help you a lot, because OpenFOAM, firstly, there is no subscription fee, it's free. Secondly, if you want to scale it up in an HPC facility, again, it's free. You can just simply buy the hardware and then put the software within that hardware, and you don't have to pay for that software anymore. So your initial cost is only going to be of your hardware. Whereas in ANSYS, you would have to buy the hardware, then pay for the software. So again, the cost margin just keeps increasing when you go with commercial softwares. Another advantage of OpenFOAM is, say later on you want to develop, or if in case you are a PhD student or a researcher and you have a certain problem that may not be possible in any of the commercial softwares, you might have to write your own code, or you may have to then resort to some other software, and you'll have to then couple each of those things. In OpenFOAM, the code that is there, you have all of the codes that are open. You can go and open any of the codes. You can make changes to them. You can modify them. You can create your own software, your own solvers as well. So all of this is possible because OpenFOAM's code itself is open to use, and you can make a lot of changes in it. Similarly, on GitHub, you will find that there are additionally many people working on different applications, and they keep posting all of their results on OpenFOAM and all of their findings on it. So you can always refer to that as well. The user community previously, if you would say 5 years or 6 years back, the user community for OpenFOAM wasn't that much. So that is why people used to not prefer to use OpenFOAM, because the learning curve itself is a little bit high. But with the use of open source softwares in the upcoming years, you have all of these applications and things. People are promoting this community. Now, there is also a downside for OpenFOAM when compared to ANSYS. Now, ANSYS has a really great graphical user interface. So as students, when you start learning, your college may give you ANSYS to learn with. But in this, you have some buttons, you click it. Like if you want to do a simple flow simulation, you just click a few buttons and then you get the output. Whereas in OpenFOAM, you may have to type in all of the parameters. So if you want velocity of 1 meter per second, you have to type 1, then you have to set up all of those things, and then you get your results. So this is one of the downsides of OpenFOAM, in which users want to just click buttons at this point, and they don't want to type in or don't want to make modifications themselves. But once you are familiar with OpenFOAM, you can streamline this process as well. So initially, to just learn OpenFOAM, it becomes a little bit difficult when compared to ANSYS. But once you learn it, then you again can do many things with OpenFOAM. So these were a few things that were there about softwares. Now coming to what exactly is OpenFOAM, what it does, and what will you be learning in this session now. So your OpenFOAM, in the word OpenFOAM itself, so you have open, that stands for open source, whereas field stands for field, whereas your foam stands for field, operation, and manipulation. So field operation meaning that you can manipulate any of the fields in your domain to behave like however you wanted based on your application. So this was developed by Henry Weller in the 1980s, and till date it is being developed. So he was from the Imperial College of London. And again, the source code of OpenFOAM is free and open source, and you can use it in academic as well as industrial applications. So the limitation would only be your physical computer that you have. So if you're able to run simulations that industries are running, then you can obviously learn that and you can run it on your system if your system can handle that. And lastly, you have readily available solvers. Again, you can access all of the codes, all of the equations that are being used by these solvers, and you can also modify them. So all of these liberties are there when you're using OpenFOAM. Now, there's another thing when you're working with OpenFOAM is you have to be clear on the fundamentals. So if you just know half of CFD and you try and run something, you may get a result. So in case of incompressible flows, you usually will get results with just half of the knowledge as well. But when you come to specific cases like multi-phase heat transfer, in those cases, if your fundamentals are not clear, you may not be able to do a proper simulation. So whatever results you're getting, you may not be able to understand it, or you may not be sure whether it is correct or not. So when you're using OpenFOAM, it lets the user have full responsibility for whatever results they get. Whereas if something goes wrong, you cannot blame the software. It is you as the user who is setting up all of those parameters. So it teaches you to be responsible with what you're putting in as an input and whatever output you're getting. Now coming to the versions of OpenFOAM. So when we had shared the installation sheet, there were two installations. One was for OpenFOAM 9 and one was for OpenFOAM 2412. So in OpenFOAM, you have two distinct groups that manage and handle OpenFOAM's launching and the upkeep of OpenFOAM. So you have the first group, that is the ESI group, and the second one, that is the foundation group. So the ESI group is a group that is more systematic. So you might have regular updates in every six months. And you can search this by going to openfoam.com, and the versions may look something like this. So you will have OpenFOAM 2412. So in this 24 is the year 2024, whereas 12 is the month. So in this case, you will have 2406, that is the June update, whereas 2412, that is the December update. So similarly, you can go for 23, 22, 21, and so on. Whereas the foundation group, now this will depend on the availability of the programmers as well and how much input they can put in one particular version of OpenFOAM. So you may have irregular updates. So you may have an update maybe in 3 months, maybe in 6 months, or maybe even in a year. So the updating of these softwares is a little bit irregular. And you can find this at openfoam.org. So you may find people just explaining OpenFOAM as .com version and .org version. So these are the two versions that they refer to. And the version itself may look something like this. So you will have OpenFOAM version 9, 10, 11, 12, and now the latest one is 14. So you can again check all of these out at these particular links. So openfoam.com, openfoam.org. Now, say you know CFD. Now you've also learned about all the softwares and you want to start off with maybe OpenFOAM in this case. Okay. So you have a flow that you have to go by. Otherwise, you may not understand what you're doing and you may not know where to troubleshoot and where to find the problem. So this is a process of doing CFD. So the very first thing is you have the problem. So in this, you define your problem statement. So say now the first case that you will see what Paris will show you, it is a simple flow over a cylinder. So that is your problem statement. So you first define a problem statement. You determine what are your input parameters going to be, what are the output parameters going to be, and what you're going to do within this problem. Once you're familiar or once you understand what your problem is, then you move on with creating your geometry and your mesh. Now in OpenFOAM, you will have to create your domain. So that is your entire volume around your geometry. So if you're running some particular simulation that requires both the geometry and the mesh, you will have to create both of these. So your geometry and your domain. So you'll have to mesh either of them or you'll have to do both of them. Okay. So say you have done this process as well. You've created your geometry, you've completed your mesh, you're happy with it. Then you move on to the next step, that is your solver selection. This is where you will choose whether you're going to solve an incompressible flow, compressible flow, multi-phase flow, or heat transfer flow. So based on this, in OpenFOAM, you will have to choose an appropriate solver that is solving for those equations. Then you move on to your boundary conditions. So this is where you will set up your input output parameters. So what you want to set at your inlet velocity or inlet parameters, what you are planning to post process. So all those parameters you can add as well. So that is your boundary conditions. Then you move on to your solution and convergence. So you've done the meshing, you've done the solver selection, you've done the boundary conditions. Now you run your simulation. So once you run your simulation, you will get some results. Those results then you can post process using any of the software. So post processing with OpenFOAM, you can extract all of the data and you can post process it using MATLAB. You can post process it using Python. You can also use Excel if you're not familiar with either of those softwares. And you can also do it using any of the other softwares that you're using. So you can do it with any other software that you're familiar with to post process all of your data. Now, say you have defined a problem, done your mesh, got a solution, put your boundary conditions, but at the solution phase, you have got a wrong solution or your solution did not converge in this case. So there are a few reasons for this. So three of the major problems that we've seen when you get an error in CFD is due to meshing, solver selection, or boundary conditions. Now, when the problem is related to meshing, you will have to go back to the step in which you had created your geometry, your domain, and your mesh, and maybe refine it, make some alterations. So maybe your mesh was not good enough. That is why your solution failed. The second reason could be the solver selection. So now say you have chosen for incompressible flow, I want to solve a particular simulation. But again, in incompressible, you may have problems like choosing between steady state and transient simulations. So based on this, also the equations change. So you have to make sure that what you're planning to solve is being solved by those equations that you choose in that solver. So you have to make sure that as well. Say you have created your mesh, you've refined it, you have selected the appropriate solver as well. Then you can move on to checking your boundary conditions. So over here, some boundary conditions may work with all conditions, whereas some cases it requires very specific boundary conditions. As we've seen for compressible flows, every boundary condition may not work for your case. You may have to use very specific conditions. Again, you have to check the equations that it is solving and only then choose an appropriate boundary condition. So again, all of this, Paris will explain it to you when he's explaining flow over a cylinder. So don't worry about this. Okay. So this was it about a basic intro of OpenFOAM and CFD. Now Paris will explain to you what exactly we're going to do in flow over a cylinder, how to set up a case and how to run it. Okay. So Paris, you can go ahead from here.
Okay. Uh, can you just confirm if I'm audible? Am I audible?
Yes, Paris, you're audible.
Okay. So I'm just pasting the Google Drive link in the chat box. So people, I'll just share my screen once. Screen share. Is the screen visible?
Yes, Paris.
Okay, so everyone, I have shared an drive link. Kindly open it, and once you open this, you will be here. Here, there will be presentations, documentation, case files, and some other PDFs as well. For this session, to access the case files that we are going to run, you have to go under case files in incompressible. There is a .zip folder, so you have to just download it. Once it is downloaded, you will be getting two files. Once you unzip it, so you will be getting these two files, that is dynamic mesh and flow cvil. So can you just confirm that if you are able to do till this step? If yes, then we can move forward. Okay. Also, the presentation that I'm going to show is already available here. So if you want to follow along in the orientation workshop in compressible flows, you can directly get access to it, install it, and follow along. Okay. So I'll be sharing my screen to my presentation. Hope you enjoy it. Okay. Is this screen visible, Ivan sir?
Yes, Paris.
Okay, so hello and welcome everyone to this basic session on flow over cylinder. This session is being introduced by FOSSEE CFD team and IIT Bombay. My name is Paris Palkar and I'm working as a research assistant at the FOSSEE CFD team. And just I'll briefly introduce to our team, Dr. Prabhu Ramchandran. Payal ma'am has given introduction to all of these people priorly, so I won't spend much of my time on it. So Dr. Prabhu sir is leading the FOSSEE project. Dr. Chandan sir, he is leading the CFD FOSSEE project. And Payal ma'am, she is working as the senior project manager at our FOSSEE CFD team. So, as Ivan sir successfully mentioned you about the OpenFOAM versions, so everyone was asking ki, which version should we use. Yesterday, we had an installation support session, whereas we helped people to install OpenFOAM. There, we had an OpenFOAM version group of ESI group. That is usually mentioned as 2412 or .com version. And one good thing about this is that we get updates very regularly, so you don't have to wait every 1 year or 2 year to get updates. So to know what does one means, so let us say someone is referring to OpenFOAM 2606, that is the latest version we have got 3 weeks ago. So the initial two lines stand for the year and the last two lines or the number stands for the which version it is. If it is 06, then it is in the first 6 months, and if it is 112, then it is in the later 6 months of the year. For this year, OpenFOAM ESI has introduced two new updates. One is the relative velocity function object. So if you want to calculate relative velocity around a particular body, you can do that. You have to they have mentioned here k in control dict in function. You have to add this command and you can compute the relative velocity. Also, if you want to add a plugin in your OpenFOAM environment, there is a PyBFOAM. It is developed by the community. So if you want to check it out, you can do that. For now, we will be sticking to OpenFOAM 2412 and 2606 or the ESI version. So what is the general procedure in a CFD problem? Let it be aerodynamic case, let it be a heat transfer case, or irrespective of the case we are working in, the process remains the same. First step is the pre-processing, where we define geometry creation, that is usually prepared in CAD modeling softwares like CATIA or SolidWorks. Then we go towards meshing. Meshing again can be done using ANSYS meshing, or in OpenFOAM we have block mesh, SnappyX mesh, CF mesh, G mesh, etc., etc. Then we have to name the patches, that which particular patch is going to work like how. Then we have to do the solver setup, that we have to select an appropriate solver for our case. Then we have to apply the boundary conditions for the particular patches that we have defined in the boundaries. Then we have to set up some numerical methods, that how stable we want our schemes to be, pressure schemes, or how good tolerance we want for our conversions. This all can be done in numerical method setup. And then we have to solve our simulation, whereas we have to monitor the residuals. It is not like if you just start simulating, you have to wait for some time and you will see the results. You have to continuously check the residuals, that if your simulation is blowing out, let us say if you are working on a transient simulation, then it will blow up. So the residuals will usually indicate this 10 to 15 times step priorly only. So monitoring the residuals is a very important factor. Same goes for time step and current number criteria. So this is just a non-dimensional number that we use, and at the end we usually do the post processing of our simulations that we have done. So now, moving ahead, let us first define our problem, that what is the problem, what are we intending to solve. So this is our fluid domain. It is in the shape of a rectangular channel. In the center, we have a cylinder of diameter 1 meter. The upstream and downstream length is based on the cylinder's diameter only. So upstream length of the cylinder's diameter is 10d, so it would be 10 meters, and the downstream length of the cylinder side would be 30d, which is almost 30 meters. One thing to note down here is key, irrespective of the dimensions that you create in your CAD modeling software, OpenFOAM will read your coordinates in meters only. So if you have created a geometry in meters, millimeters, you have to either scale it to meters or you have to scale it down. So that is the one catch we usually make in setting up the OpenFOAM. Uh, so, and a general OpenFOAM case structure, I want to explain it to you. Please don't get overwhelmed by watching all this. So usually if you have set up all these things correctly, then you are good to go to set up your own case. Okay. So there should be three important things. That is firstly 0.original or the zeroth folder. Uh, as we know that we are solving partial differential equation, and Navier-Stokes is a PDE. So for that we need a initial condition and a zeroth condition. So because of that, this is known as the zeroth folder. Coming to the constant folder stands for key in your simulation. These things or these files are going to be constant throughout your simulation. Hence, it is known as constant, which consists of polymesh. Polymesh stores information related to your mesh, then transport properties related to your fluid that you are using, and turbulence properties if we are including any. Uh, this is only mentioned that zeroth folder contains all the information related to your boundaries. Then this contains information related to your mesh. Also, if you are importing any geometry from any other CAD modeling software to your OpenFOAM environment, constant folder is the place where we have to place our geometry and work on it. Then we have the foam.foam file. This is the paraview readable file. So to connect paraview with OpenFOAM, we usually use this. And then there is the system folder. In system folder, you have information related to your simulation. That is for how long you want to run your simulation, what will be your start time, end time, what schemes and numerical tolerances that I mentioned in the step 2 here. In step 2, it is all mentioned in the system folder under FE schemes and FE solution. There are many files that you can include under systems folder, but as of now, we have this only. So this is the mesh of our CFD domain that we have meshed. Can any one of you just confirm that if you have downloaded this file, and if yes, we have to paste that file into our run directory. So is everyone able to follow along till this step? So let us say now I have OpenFOAM 2512. I am sourcing it. Let me zoom in my screen. Is the font visible?
Yes, Paris.
Okay. So I have to just write run. After sourcing the run direct OpenFOAM environment, I'm just writing run. So now I'll be redirected towards OpenFOAM. This is my system name, after OpenFOAM version name, and inside my run directory. So before starting, can every one of you confirm that are you used to Linux environment or you are new to Linux environment? If you are new, then I have to tell you some specific commands as well that you will be facing for the first time. New, okay, new to Linux. Okay, fine. So okay, understood. So every one of you is able to follow along till this step. Have you sourced your run directory? Okay, okay. Now there is a command called explorer dot exe space dot. Okay, explorer, there is a space in between and then there is a dot. Okay, so you have to do this. Is everyone able to follow along till this step? If yes, then you have to just hit enter on your terminal and you will be opening your OpenFOAM environment's run directory through file manager mode. Okay, so you have to do nothing. You have to just go in downloads, copy these two folders and paste it here. Paste it. So has every one of you are, if you have done till this step, just let me know. So just go in this drive, copy the folder. After copying, extract it. After extracting it, paste it in your run directory. Okay, I'll go a little slow. Yes. Okay. See, this is the drive link that I'm sending it here. Okay. Kindly access this link. I'm pinning it as well. So kindly access this link. Once you access this link, there will be case files. Okay. You have to go under case files. Once you go under case files, there will be two folders. One is incompressible, another one is the heat transfer. So you have to go inside incompressible folder. Okay. And just install it. Okay. Once this is installed, you have to go in your download section, extract it, maybe using WinRAR or whatever versions, whatever file extractor you use. After extracting, you will be getting these two files. Okay, I'll show it to you as well. In this folder, we have two files. One is flow over cylinder, and another is the dynamic machine file. So you have to just extract it somewhere. Once extracted, you have to just copy these two files and paste it in your run directory. And how to source the run directory? Go in your terminal. If you don't know how to open terminal, then you have to go in your PowerShell. Once you open PowerShell, then you have to write WSL. Once WSL is loaded, then you have to write. Now I have 2512. You may be having 2412 or 2312 or 2406, any of that. So if you have set up an alias that we have given in the installation sheet, we usually write 2512 or 2512 to source our OpenFOAM. Once this is done, then we have to just write RUN. This is the same thing that I was showing previously in this terminal. So can you just give me a thumbs up if you are able to see it here? Okay. Uh, okay. So people are able to do it. Okay. Uh, Mr. Rohit, you can write your query in the chat box. Okay. Slow. Okay. Mr. Rohit, yes, I'll try my best to go a bit slow. So here we have two folders. You will be having two folders. Now I have various things as well in my run directory, but you should be only seeing the flow cylinder and the dynamic meshing file. Okay. So first go inside flow cyl folder and you can see all these files. Okay. Now to view them in the terminal, we have to, let us say if you want to go inside any file, so you have to do cd. Now I have to go inside workshop as well. So if you want, now you should be seeing like this in your terminal. To view what is in your run directory, you have to write ls. Okay. Once you write ls, then you should be seeing these two files, dynamic mesh and flow cyl in your terminal. Can everybody see it? Okay. Okay. Uh, okay. Okay. So let us say if you want to go inside dynamic mesh folder. So in terminal, what we do, we write cd space dynamic, and if you just write dyna and hit tab, the OpenFOAM environment will try to understand what I'm trying to do. So it is understanding that I want to go inside the dynamic folder. Okay. And hit enter. Now I am inside the dynamic mesh folder. Similarly, if you want to get out of this folder, you have to just do cd space dot dot. And now you are in your run directory. Now here I have two folders. So that is why you will be seeing workshop. But for now, we have to go inside flow cyl. So we will just write FLO and hit tab. Now it has understood what I'm trying to do. I want to go inside flow over a cylinder. Hit enter and do ls here. Now this is the terminal way of watching things. If you want to view it in a file manager mode, again, as I said, you have to do explorer dot exe space dot and hit enter. Now here there are same files only: 0.original, constant, system, all run, and foam.foam. Here also, if we see, if and here I was inside flow cyl. Here I was also inside flow cyl. So there was 0.original, all run, constant, foam.foam, and system folder. Is everyone able to follow along till this step? Okay. Okay, fine. Thank you, people. So here you have to do nothing. You have to just write block mesh. Block mesh is a file that will help you create simple geometries, but because of time constraint, I won't be able to show you the file. You have to just execute the command called block mesh, and the case will run. Your mesh will be created, and to view it in paraview, you can see it like this. So say if I want to visualize my mesh, now you may be having paraview installed in your Ubuntu only. So if you want to view it from here, you have to write paraview here. But now I don't have paraview installed. Hence, I usually use the manual way that I have installed it in my system file only. Now, what you can do is once you are inside the flow CYL, you have to go here, right click it and copy the address. Okay. Once you copy the address, go inside paraview. On the left upper corner, there is a file called file and there is an option of open. And inside the name section, you have to paste the uh, address of your file. So it will tell paraview to look inside this folder. Now to visualize our OpenFOAM simulation, we usually use .foam folder. I personally prefer to name it foam only so that it avoids confusion. Okay. So I'll just write foam.foam, I'll hit OK and I'll press apply. Now my body is being loaded here. Is everyone able to follow along? Actually, Mr. Avinash, sir, actually we have the time constraint. That is why I have to move it. But okay, fine. Please tell me which step you haven't understood. No, Srividya, we don't have to go inside dynamic mesh. We have to go inside. So on the terminal, see, there will be two folders. One is the dynamic mesh and another will be the flow cylinder. Okay. We want to go inside flow cylinder as of now. So for to go inside any folder using terminal, we have to write cd flow and then cval and just hit tab. If you just write flow and hit tab, it will on its own understand that what we are trying to do. Okay. Now you see I am inside flow cval. So previously I was in OpenFOAM, my version run, and inside the run directory. Now currently I am inside flow cval directory. If I list out what things are there, so there is 0.original, all run, constant, foam.foam, and system folder. Here you have to just write block m capital mesh and run it. I'll paste the command here as well, block mesh, so that you have to just copy this command, go inside flow cval and paste the command here. The people, this is just to get a brief idea about OpenFOAM and how useful OpenFOAM is for your simulation. If you are not able to follow along, please do not worry. Inside PPT, all the steps are given to run the case. Okay, so please do not worry if you are not getting. Please scroll down. Uh, I'm not getting you, Mr. Abhijit sir. Even if you're not able to follow along with me, after this session, the case files, the presentation, everything is available. You can just open the terminal inside E. So you have to, Mr. Parag, Parag Moni, you have to just copy the folder and you have to paste it inside your run directory. So say you go here, you have downloaded inside anywhere, you extract this. Once extracting, you have to copy these two files. After copying, you have to direct navigate to your run directory that I explained, using how to open it using explorer.exe, and paste it here. After pasting on your terminal, you have to go inside flow cval. Okay. Once this is done, you have to do nothing. You have to just write a command called simple form. Now we are running this case using simple form, but there are multiple solvers available, but you can check out after the session. Once you write simple form, this one. So you have to copy the 0.org folder inside the 0 folder. Now you'll see there are 5 folders, 6 folders. So this is the command to copy the 0.org folder. So run this command on your terminal. Once this is done, just do simple home and hit enter, and the simulation will start to run. Now if I a bit zoom out, now you can see it is solving for time 156, time 157. This simulation is bit easy, hence it is going very fast. So you can visualize this. This is the monitoring of the residuals, and see it has ended at t is equal to 500. Now if you are wondering why it ended at t is equal to 500 only, so there is a reason for that. As I mentioned, there is a folder called control dictionary. If we open it, so here it is explicitly mentioned that simple4 is the solver we are using. We are starting from start time. Start time is t is equal to 0 seconds. And we have to stop at end time. End time is our 500. Hence, it stopped at t is equal to 500. Okay. And right interval is the parameter where we are writing information of our simulation at every 10 time steps. So if you can see, first is at 0, then 10, 20, 30, 40, so on and so forth. Say if I change this to 50 and run the simulation again, then this will store information related to my simulation at only 50 parameters. So if I refresh it, now I have to clear this and again save it. It will take some time, and as I can see, we are already running late. So this is just a way of explaining, and rest of the things we are keeping it as default. Okay. Is everyone able to follow along till this step? If not, please let me know. I'll explain you if you're facing any issues. Okay. Okay, Mr. Vivek. Uh, Arihant, what is the issue? You can paste it in the chat box. Okay, so to copy the org folder, wait. So your case structure will almost look like this. We have to do nothing. We have to just copy it and paste it here only. Okay, this will be named as 0.org underscore hyphen copy. So just rename it. You can rename using terminal. You have to just name it as 0 and it will be present here. If you want to do the terminal way, you can do cp-r 0.org to 0. Both are the same way only. There is not much of a difference here. Is everyone able to follow along? Can you just scroll over all the... Okay. So if anyone is forgetting any commands that they are using, so for that on terminal, there is a command called history. So this will give you the list of commands that we are running on our terminal. Okay. So ParaView step once again. So if you have installed ParaView, you have to go inside ParaView. Once ParaView is open, in the left upper section, you have to click on File and Open. Once you go till this step, you have to go inside your FOSSEE folder, copy the address from the top that is available here. This is your Linux environment, Ubuntu 26.06. In your system, it may be 22.04 or 24.04, depends. Then home, then this will be your system's name, OpenFOAM. Then this is my OpenFOAM version, run folder, and FOSSEE. So you have to just right click it here, copy the address, and paste it inside here. Once you navigate it till here, home.foam, okay, and hit apply. Okay. So I'll just quickly run this case once so that I can show you some of the basic post processing. If you are not understanding, it is okay as well. Initially, OpenFOAM is quite difficult to understand. The learning curve for OpenFOAM is quite steep. You may take some time to understand what one folder stands for. Sharing this. Yes, sure. Yes, the session will be shared. Okay. Now, I'll go inside one of the paraviews and delete it. And I'll load the form.form folder. Now, if you can see, it has stored every file at every 50 iteration. Why? Because I had changed this write interval to 50. Previously, it was 10, but now I have changed it to 50. Okay. So I'll just hit OK now and hit apply. Inside properties panel, there is a green icon called apply. I'll just press apply. So I'll change to maybe pressure and I'll switch it to 2D. So can you guys see this on your systems after opening ParaView?
Paris, can you increase the font size?
Font size, screen size?
Yes, the overall display size.
Okay. So is it visible now?
Paris, I think you can increase the scaling to 125, it should work.
Okay. Now?
Yeah.
Is it fine?
Can you change the resolution 720?
720.
Bharat is 1280, 720. 1280, 720. Need below.
This one?
Below.
Okay.
And this one.
Okay.
And 100%.
Okay, it is 100%. Now, is it visible? Even sir, can you?
Yeah, it's better.
Okay. Okay. So, people, are you able to follow along till this step? Okay. 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 So this is the our usual paraview environment that we usually see. So this is called the upper ribbon, where we have some technical functionalities. When you will do some advanced post processing, you will be requiring this. So for now, if you just want to play along with your simulation, currently we are at t is equal to 50 because we have written our simulation at every 50 intervals. Okay, and here it is a button called play. You have to just play it. Okay, if you play this simulation button, it will run your simulation and you will be seeing some vortex shading behind your cylinder. Can you guys see this? Okay, other than Mr. Girishankar, you have to do nothing. You have to just go in file, open, copy the address, and open the foam.foam file. The foam.foam file is already inside the zip folder. Just hit OK and press apply in the properties panel. So are you guys able to do along till this step? Okay. If yes, then you have to just press apply. In the upper ribbon section, there are two parameters. Here you have the cell values and total cell values, and here we have the inside cell values. So we'll just change it to pressure, and let's say we want to go at the first time step. So we are at t is equal to 50, and if I want to run the simulation, you have to just play, you have to just select on uh, the play button so that your simulation will run. So here we can see a little bit of vortex shading is happening. If you want to visualize your how your mesh looks, so inside this surface panel, change this out parameter surface to surface with edges. So this will be your mesh. Okay, you can visualize it through this as well. So how clear your wake refinement region is captured. So to capture wake, we have refined this section so that any eddies or wakes that will be forming, we can capture them accurately. So this region has been meshed even better. You can run this simulation for a longer time as well. In your control dictionary, you have to change the 500 time to say 1000, or it's up to you for how long you want to run it. Save it. So instead of 500, just change it to 1000 and run it. Okay. Uh, Hopefully, Mr. Akula, you have got this step. If not, I'll tell you again. Is it clear, or you guys are having any issues or doubts? Okay, Aditya, do you have any doubts? You can unmute and ask. Can we monitor? Yes, yes, we can do that. So there is a parameter inside OpenFOAM. It's called checkmesh hyphen write all fields. Once this is done, uh, you can visualize all of your mesh quality parameters as well. So I'll just change this to open foam.foam, skip 0 time, and here it will come. As we have run the simulation now, it is not coming, but while meshing, it will write everything to the foam.foam file. You can visualize it. Yes, yes, Mr. Rajaram, we have to do this only. Correct. Uh, as I can see, We are already running out of time. So maybe I'll skip the dynamic mesh part, but please do not worry. You have to do nothing but the same steps that are there. I'll just tell you how to run the case. Now here the block mesh file is also present. So you have to just copy the zero.original folder inside your zero folder and just run simple foam and the simulation will start. Okay. So you have to do nothing, and I have inserted these commands inside our folder as well. So you have to just copy it and paste it and just run the case. So everything is available inside the file. So please do not worry if we are not able to cover it up. Is it okay, Ivan sir, or should I take some questions?
Yeah, I think we can take one or two, or we can take all
Okay.
at the end of the session.
Fine.
Yeah, the last 10
Fine.
minutes are, I think, dedicated to Q&A.
Okay.
Yeah.
Okay, Ayush, are you having any doubts? Maybe you can unmute or paste your queries in the chat box. Any questions, any queries, if you are facing, you can just write it in the chat box. The team is there to help you out. Okay, Aditya. Concept is clear. Okay. Thank you, Mr. Raji. So maybe if there are no questions or if there are any, you can paste it in the chat box. I'll take it. But for now, I'll be stop presenting my screen. Okay. Thank you. So what happens is, let us say if you are working on a multi-phase case, or if you have a multi-phase case or any overset machine case. So if you just keep the zeroth folder, your initial and boundary conditions will be removed if you run the block mesh folder or snappyx mesh command. So that we have to retain what were our initial boundary conditions and run it. So this is the reason it is a very good approach to uh, copy your original folder and then save it. Uh, yes, the recording will be shared. Yes. Do I need to close ParaView to run simulation? No, no, no. You can do it simultaneously. It's not a problem. Okay. Can see cases only, but what is the process of changing the parameters? Like, so for that, if you want to change your velocity or anything, so there is the zero.org folder. You can change inside this file, this part.
Paris, I'll show that. Don't worry.
Yeah, sure.
Yeah.
Okay, so I'm stopping my presentation. Ivan sir, you can take along, and if anyone has any doubts, just let us know. Yeah, it's fine. No problem. Aryan, it's fine. No problem.
Okay. Thank you, Paris.
Yes.
Yeah. So can you just confirm whether my screen is moving front back and it's visible?
Yes. Yes.
Yeah. So again, good evening once again to everyone. So now we'll just quickly look at a case of heat transfer. I'll speak about all the questions that you have about how to set up a case as well. So regarding how to set up parameters and all of those things as well, we'll see that. So firstly, why do we do heat transfer? If you want to do HVAC cooling and all of those things, design optimization and any of the other things, you usually do heat transfer to understand how heat is transferred from point A to point B in a system. Now, these are a few applications again of heat transfer. So this one is a compressible flow, a flow over a cylinder. So this is again compressible. So you have heat. This is a centrifugal compressor, and these two are just a simple heat sink heat transfer. Okay. Now the modes of heat transfer are again conduction, convection, and radiation. And right now we'll see a simple case on conduction. So this is the equation. So again, as I said, that we have these physical equations. So this is the conduction diffusion equation that we have. So this is your conduction and diffusion part. Whether this is the heat source part. Okay. So you have a source term, and this is the way we usually write it in the way that we understand. But in OpenFOAM, if you open the backend code, it's written something like this. So if you go and see the simple equation that is written over here, so you have dou T by you have dou for temperature T, and then by the dou T. So over here it's written d dt of T. Okay, so that is your derivative of T. Then you have alpha, that is your diffusivity, and you also have the Laplacian term, and then you have the temperature term. So again, this Laplacian term is again written over your FVM Laplacian, and your dt, that is your diffusivity. So this alpha is written as dt, and then you have the temperature term, that is T. Okay. So again, this is then your source term that we have. So over here, we will be calculating your volumetric heat generation. And along with that, you also have your density and you have a specific heat. So all of these parameters that are there over here, you can put that all in a file called FV options. Now in OpenFOAM 9, whereas in OpenFOAM 2412, this particular file will, the name itself will change. So in OpenFOAM 2412, the file name will be FV options, whereas in OpenFOAM 9, it is FV models. Okay, so again, from the drive link, whenever you download it, I've kept both the versions for OpenFOAM 9 and for OpenFOAM 2412. So whichever version you have on your laptop, that is the ESI or ORG version, you can download according to that. Now, this is the problem statement that we have. We have a simple cube, or we have an elongated cube. This is your side 1 and this is your side 2. Both are set to temperature 0, whereas the center we are giving a heat source. So this is the value for the heat source, and we have the diffusivity. So based on the diffusivity, you can calculate your material and all of those things. So this is going to be high temperature. These two are going to be low temperature, and the overall size is around 1 meter. So based off of these values, we calculate some of these parameters. So in OpenFOAM, you will require the diffusivity value and you'll require the source term value. So these two values will require to run the simulation. Okay. So where exactly to make changes, how to copy the file and everything, Paris has shown you. So these are the commands that you can directly run it in your terminal to copy the files. So for OpenFOAM 9, these are the paths that you have. So you have to copy a pre-existing tutorial, then make modifications to that. In this case, we have given you the tutorial case files as it is. So you can just run that. But in case you want to do it from scratch, you can go to these tutorial links and you can just search them, or you can just run this command in your terminal itself. So that was for OpenFOAM 9, and this one is for OpenFOAM 2412. So again, the tutorial path is a little bit different for each of these cases. So again, you can check that. And this is for the FV models. So FV model, FV option, based on the version, you can make those changes. So over here is FV model, this is the path. For FV options, this is the path. Okay, so we'll copy that. I'll show you what we're going to do with that as well. So now for people who are asking, how do we change the mesh, or how do we change mesh parameters? So in your system folder, so you have 3 distinct folders over here. So I'll show that as well. So what you can do is you can go to the drive and you can go to the link over here. Let's close this. Case files under heat transfer. You can download any of the file that you have. So for OpenFOAM 9, this is the zip file. For OpenFOAM 2412, this is zip file. So again, the same procedure, download it, extract it, and copy it to your run directory. So in my case, I have copied it to my run directory. So this is my OpenFOAM 2412. Now again, where exactly is your run directory? So Pari showed you a quick way to just type in your terminal. But in case you did not understand that, it's fine. So on the left-hand tab of yours, so you see over here, you can scroll down to the very end. You'll find this Linux icon. Click that Linux icon, and then you will have Ubuntu 2204. So click on Ubuntu 2204. Under that, you have Home. Under Home, you'll have your user ID. Under user ID, you will have OpenFOAM. And under OpenFOAM, you can choose which version you have. So you guys might have just 2 versions, OpenFOAM 9 or 2412. Now I have different versions, so I have more files. So in this case, we are going to OpenFOAM 2412. So I'll go to the run directory for 2412 and then run. Okay. Now in my case, again, I have more files, so you will just have one file which you paste it over here. So you have to copy that downloaded file and paste it in your 2412 or OpenFOAM 9 run directory. Okay. And within this, I've saved it now in orientation workshop and over here. Okay. Now, don't worry, it's fine if you don't get it. There is a in-depth tutorial on how to set up a case, how to do block mesh, how to do snappy hex, how to set up and run an incompressible case. So all of that links where it is, I will show you that as well. So don't worry if you are not getting it right now, it's fine. Okay. So again, in your folder structure, you will have 3 files. This is the result file. One is clean file, one is done file. So you can open the done file. So here you will have 3 distinct files, 0, constant, system. So 0, it will hold all of your initial boundary conditions, constant, all your fluid properties that you have. So in 0, you will have your temperature in this case. If you were running the flow over a cylinder, you would see that you have velocity U, you have pressure as well. So velocity and pressure are also there. But in this case, we're just solving for temperature. So just temperature file. Then you have constant property. So this is all the properties that remain constant throughout the simulation. So you will have transport properties. So these will be your fluid properties themselves. So in this case, we have to give diffusivity. And in case you're running again an OpenFOAM incompressible case, you will have the kinematic viscosity value that you would have to define over here. So again, that you can open the file that you've just downloaded and you can see that as well. And in this case, we have this FV options. As I said, for 1D heat conduction, we will require to specify the heat source. So the here is where you will specify your heat source in this file. And lastly, you have the system. So all of your simulation parameters, your mesh file. So your block mesh dict will be your mesh file. So you're creating a mesh using block mesh. So in this case, I will open this. So again, we have these additional parameters. So the same thing is in the presentation as well. Now in this, we have convert to meters. So we are just scaling it down from 1 meter. So again, this is scaling it from meters to whatever value you set over here. So in this case, we want our end result to be around 0.01 meter, 0.1 meter, sorry. And based on that, we specify the vertices. So again, how we define these vertices, what is this block doing? I'll show you how this is done with an example. Okay. So let's open this file once again. So let's say I have, yeah, so this is my block mesh. Okay, I'll just pin it over here. Yeah. Okay, let's make it a little bit big and place it over here. Now over here, I have in ParaView open. Okay, so this is my cube. I've just made it in skeleton view so that you can see inside it as well. So what do we mean by these vertices? Okay, so the first you will define in ParaView in block mesh, that is your vertices. Okay, so this is 0.0, this is 0.1, then this is 0.2, 0.3, 0.4, 0.5, and so on and so forth. Okay, so at 0.0, your 0.0 should be at origin. So this is the origin. So if you see over here, you have 0.0 over here. Whereas 0.1 is set at a distance of 1 in the x direction. So my 0.1 should be around there. But now since I've added this scaling factor, so in ParaView you can see that the value will be around 0.1. Okay. Similarly for 0.2, it is at a distance of 1 in the x direction, whereas at a distance of 0.1 in the y direction. So at 0.1, again, you scale it down to 0.1 multiplied by that, you'll get 0.01. So if you zoom in over here, you'll be able to see that 0.01 over there. So if I just move it, yeah. So again, it's just coinciding with the other point. That's why you'll be able to see a 0.1 at sometimes, you'll be able to see 0.01 at some point. Okay. Similarly, 0.3, that is this point, at a distance of 0 in the x, whereas only in the y direction it's at 0.1. So you scale that to 0.01 with the scaling factor. Now the remaining points are just an extrusion of the first 4 points that you define. So in the z direction, we've given it a scaling factor of or a depth of 0.1, and then we've scaled it down by 0.1 again. So that is why you get this particular object. Now that is defining your vertices. So I've defined 8 points. Those 8 points make my block. So under blocks, I want a hexahedral block. So under that, I will specify all of these vertices. So 0, 1, 2, 3. Based on this, you will get your orientation. So again, how you define this, the number of cells, all of those things are explained in a proper tutorial just meant for block mesh. It's a proper 1-hour tutorial. You can check that it's in depth. You can see that, you can learn it from that. There's no problem in that. Okay. So don't worry about now not understanding this. So to explain it in simple terms, your this coordinate system will determine your x, y, and z coordinate system, how you define this block. And the next thing you can define is the number of cells. So in this case, since we're doing 1D heat conduction, we only are defining the number of cells in the x direction, whereas in the y and in the z, we've only kept 1 cell, because again, we're solving for a finite volume method. So it requires just 1 cell in either of the direction in which we're not solving as well. And lastly, we have simple grading. In this, you can add an inflation layer. So for people who have used ANSYS, they might know inflation layer. So whether you want your cell size to increase or decrease in a particular direction, you can do that change using simple grading. Lastly, you have boundary. So this is where you will define your boundary face or your boundary patch name. So in this case, I have this left side as side 1 and this one at side 2, this one. So I define that, I again determine the points that make up this face. So if you see for this side, It's made up of 0.5126. So if you see over here, it's made of 5126. Again, how you name it, the orientation, all of that is explained in the tutorial. You can check that. Okay. So this was about just brief intro on block mesh. And again, the type that we set is wall, and anything you do not define. So say anything around here, it will go as default empty. Okay. Now coming back to the presentation. Yeah, let's close this. So this was about block mesh. Okay, so you have side one, side two. Now you set up your boundary conditions and physical conditions. So in this case, you can open the T file, and then you can see under side one, we've given a fixed value, uniform 0. Similarly, for velocity also, you have a type fixed value and then uniform, but you'll have to give obviously a vector coordinate. Now, since time for your temperature is scalar, that is why you only have one value. Whereas for velocity, so it's a vector, so you'll have the x, y, z coordinate system for that as well. So in this case, you just have side one uniform value of 0, side two uniform value of 0, and then default faces we've kept as empty. Similarly, for under constant under transport properties, you can set the diffusivity. Now over here it's set to 1, but based on the problem statement, you can just cross check it and put this particular value for diffusivity, 1.15 into 10 to the power minus 4. Okay. And yeah, then once you copy that FE models, you have to make some changes in that to add a heat source. Okay. So in this case, this is the original file. And once you modify it, you'll get something like this. Under this, you'll have an energy heat source, the type that it is, selection modes. Now in this case, we want to add the heat source in our entire domain. That is why we set to all. If you want to specify to just a specific patch or a specific area of your domain, you can specify that as well. Volume mode, again, specific. And sources, we are giving a temperature. So temperature source explicitly, we are determining 0.295. So again, this value we calculated based on the input parameters that we had. Now, once you set all of that up in your control dict, you can specify that will hold your solver name. So in this case, we're using Laplacian foam. Then you can set your start time, end time, delta t. So your delta t will be based on the dimensionless number, current number that Paris was talking about. So again, once you learn CFD, you will understand that much better. Again, all of these things are explained in each of those tutorials that we have, 1 hour each. You can check that out later on also. And solution, you can either change this from a steady state solution to a transient solution as well. And where do you do that change? Under system, again, you'll have FV schemes, FV solutions. So FV schemes, you can change all of these parameters. Again, there's a dedicated tutorial just on numerical schemes, so you can check all of that out. So each of these parameters, what they're doing, how you can determine it, all of these are explained in the tutorial. Okay. In case you don't know what to do, just make a spelling mistake. OpenFOAM will list it out for you that these are some of the values or some of the default types you can use. And if it's not from this, then it will obviously tell you that these are only the types. You use one of these. Okay. Now to run the simulation, the commands are simple: block mesh, Laplacian foam, and then to view it, parafoam. Okay. So say you have already copied this particular folder in your run directory. So the very first thing you can do is, so I'll open the done template. Now there are two ways you can view or you can access this file. You can either right click and open in terminal. Once you do this, you will have to then type WSL. That will launch your Windows subsystem for Linux. And then type OF2412. That is your sourcing, your OpenFOAM version. So in this case, I'll just zoom in. Okay. I'll just type ls to list. So in this case, I have 0 constant system. Now this is one way. You can just right click in your folder and you can open it in terminal. The second way is you can search Ubuntu. So in this case, search for Ubuntu 22.04. Then first what you will do is, now in this case, since you're already in the Ubuntu environment, you don't have to type WSL to enable your subsystem. So I'll just directly type OF2412. And then I will type run. That will take me to my run directory. Now within my run directory, I will have to access the file. So that is under CD. Then it was under orientation workshop. Under that, it was 1D heat conduction case. And under 1D heat conduction, it was under 1D heat conduction case done. Okay. Okay. So again, in case, okay, so it is under template, and then done. Yeah. Okay. So now I am inside my actual case file. So this is the second way that you can do it. Third way, launch it through PowerShell and type WSL the way Pari showed you. Okay. So there are multiple ways to access your file. So these are two of the simplest way. So I'll just go ahead with this one. I'll just close this. Yeah. So now I am in my case file directory. So I will first do block mesh. Once it is done with block mesh, it will give me a basic info of what my mesh consists of. So it will say that it has blocks, the number of blocks. This is my bounding box. So scaling is set to 0.1 in all directions. It will give me my bounding box. So it's from 0.1 to this particular point in space. Number of points, number of cells, number of faces, number of internal faces. So all of these values you can get. It will also list out all of your patch names that you have. So in this case, it is patch side 1, side 2, and default faces. So these are the names that we have given. And based on this, we have given on these particular patches, we have given a particular boundary condition. Now to run the simulation, you just type Laplacian foam and press enter. Now, since the simulation is just a 1D heat conduction and the end time itself is quite low, it runs almost instantly. And to view your simulation, you can type parafoam. Now you can either type parafoam directly, or you can also do touch and add a name that you want. So in this case, I will just add my own name, evan.foam. Okay. And I hit enter. Now, once I run this, I can reload it. So if I would have not done touch, this particular file wouldn't be created, a .foam file. But since I ran this command, touch whatever name you want to set .foam, it set or it created this particular paraview file. Now I can directly open this file in paraview, or I can open it through the terminal as well by typing parafoam. Now, when you do this way, when you type touch your name .foam, and then you manually open it from here. So in this way, your paraview is launched separately, and whatever you make, whatever setup you've made over here, and then say you want to again run your simulation, you can run your simulation over here, and you can just right click and reload the files, and it will reload everything within this. But if you directly type over your parafoam, it will block the terminal. Like you won't be able to do anything else unless you close that particular file or something like that. But again, it depends on preference. If for you paraview or parafoam command is directly convenient, you can do that. If for you this particular way is convenient, you can do that as well. Now, say I've opened it, I've done my simulation, I've opened it in paraview. I'll switch from this to T and surface. So this is my surface with edges. I'll show you. So the number of cells are 100. So again, it's only in the X direction. If you want, you can also do this 1D heat conduction as 2D. So you can specify the number of cells in the Y direction as well. So you can check this out. The files are with you. You can make changes. So when you see the videos and you're familiar with basic commands of Linux, OpenFOAM, you can make all these changes and you can run it. So for now, we'll switch to temperature and surface. Just and then hit OK. Yeah, okay. So in this case, it's steady state. That is why you won't see any changes. So if I want to make some changes in this case, so under FV schemes, if I change it, I'm not sure if I change it to Euler. Yeah. Okay, so you can, if in case it is steady state over here, you can change it to Euler. And then you can also make the changes over here. So in our case, we had set the diffusivity. So under properties, so diffusivity was set to 1, whereas when we calculated it, it was 1.15 into 10 to the power minus 4. Okay, so you can try this as well. Make the changes and then rerun the simulation and see whether this thing changes. Okay, so by default it should change. So you will have a heat source over here, and then it will start moving towards the cold points of your simulation. So let's do that once more. I've changed that. Just block mesh, Laplacian foam, and then parafoam. This time I'm using parafoam directly. let's see, T. Yeah. Okay. So in my case, it's like there may be some problem as well when I was setting it up. But again, if you run this, you should be able to see the change from a high temperature to the low temperature. You can also plot all of this graph and you can post process it. Again, there is a dedicated instruction sheet on that. You can do that as well. Now I keep saying that there is the sheet where exactly you'll find it. So in the drive, if you go to the orientation part, so there is this FOSSEE learning material. You can click this, and within this you have a set of links. So again, the course that we've given to VIT Vellore, that is available on YouTube. So each of those course sessions are around 1 hour. So it starts from block mesh, snappy hex, setting up an incompressible case, setting up compressible, up all the way up to solver modification. So you can check this link, and all the files that we are using during this course, the drive link for that is also given over here. Same for spoken tutorials. We have a spoken tutorial that teaches you OpenFOAM from scratch. So you can check these links out, and all of the previous workshops that we've taken, basic workshops, faculty development programs, and even advanced workshops. So all of those are available over here. Along with that, there are also documentation links. So that is for the ESI version and the foundation version, and along with that also post-processing functions. So once you go through this particular course, you'll be able to understand where exactly are you supposed to use post-processing functions, how you're supposed to use them, and what changes you can make and what you can make and you should be doing in OpenFOAM. Okay, so just go through these links once, and yeah. I also have one thing to show you, that is the site. Now you can search our website, that is cfd.fossee.in, and it will take you to this particular site. So as Payal ma'am was saying that we have different faculty members and advisory boards. So all of the information is over here. Same goes for the advisory board. Along with that, we also have a repository. So on the left-hand side, we have a case study project and we have a research migration project. So if you scroll down to completed case studies, so over here, you can download any of the case files that you want that is being done or has been done by students like you. So during the internship, or even when people are studying or trying OpenFOAM and they want to publish their work, they make their files. So I'll show you this one. So you have this particular file. This is done by an intern, I think last month. So in this, they have worked with a professor. You can also work independently and submit a file. So when you submit a file, someone who's later on seeing or wants to try and replicate this particular problem, you can first download the abstract and you can go through that. You can then read whether it's for you or not for you. If it's similar to your case, then you can download the entire case study. So now this case study, once it's downloaded, you'll be able to see that it will have the complete report. Yeah, so it's done. So under this case, you will have the case files and you'll have the report as well. So if I open this, so you have the report. So again, whatever work they've done, everything is explained in detail. All the boundary conditions, all of the parameters that you require to understand, to use all the equations, everything is mentioned in their report. Along with that, you also have the case. So in this case, he's done diesel surrogate combustion. So that was for 0D and this was a flame speed. So you can download all of this and you can run it in your own system. How you want to run it, there's also a README file. So in this, you have a set of instructions on how to run this particular case, what parameters you should be changing if in case you want to see that particular output that is mentioned in the report. So all of these parameters are explained. Which version of OpenFOAM we are using, sometimes they also mention that. So that's handy for you if you're using maybe the ESI version or the foundation version, you can then switch between them based on the tutorial that you're trying. So this was about the case study. Similarly, for research migration, you can check the completed research migration. And over here, you have all of the cases. You can download them. You can run it on your own system. And say if you have your own project, say you already know OpenFOAM or you've done some work in OpenFOAM and you want to publish it, so that later on if someone asks you that whether you know OpenFOAM, you can directly share the link over here. So whatever files over here, it will show your name, it will show the title of your project, and it will also show the university that you're assigned to. So if anyone asks you that whether you know OpenFOAM, you have this proof that I have done it, I have submitted it over here, and they can access that. They can even download the case files and see for real if you are able to do it or not. So say you want to submit your own project, you can go again to the research migration or case study. The procedure is same, and go down to procedure or to submission. So again, if you want to see the procedure, the whole procedure will explain how you're supposed to do it. Then you can go to submission guidelines. So first you will have to submit a 1-page synopsis. So this will be your abstract, a 1-page abstract of what exactly a problem is, and make sure that you follow again the research migration and the case study format that is there. So this will have your title of the paper, name of the journal or publication, authors, and your chapter volumes. And again, if you want to see a sample, there's a sample over here as well. Then to prepare the report itself, so you will have firstly your case files. The case files will be in your zip file, so that will consist of all your template files. So you'll only have your zero constant system and any other supporting files. So as I said, you can do post processing in Python. So all of those Python files, you can add it as a submission file as well. And there are some additional parameters, some additional things that you have to keep in mind when submitting. So those are, you should be at least above. Now this is an older update. So that is why you would have to, for now we are keeping everything above OpenFOAM version 9 for the foundation version, and everything above OpenFOAM 2212 for the ESI version. And also for foam extent. So if you want to do FSI problems, fluid solid interactions, you would require foam extend. Or if you want to do something like immerse boundary method or ALE methods, so all of those things can be done in foam extend. Again, contours, plots, datas, if you want, you can add them if they are relevant. If they are not relevant, you need not add those. And your report itself, again, there's a template over here. You can see that, you can follow that. And once you've done, you say you've created your report, you've kept your files ready, you've submitted your abstract, it's got approved, then you can go ahead with the proposal. So before that, again, for your abstract to get approved, you would have to create your username. So I'll just log in and show you. Yeah. So if you want to submit a proposal, again, this is the procedure. You can add your title, whether you're Dr., Professor, Mr., Miss, your name, your email ID, your university name, and your institute at which your university is associated with. And how did you come to know about the project? Some basic info, the country that you are from. And then over here, you can add the source of your project. So if you're doing a research migration, you have to validate your results against a pre-existing or published paper. So that name you have to mention over here. Then the OpenFOAM version that you have used. Similarly, the simulation type. So here you can choose the solver that you have used. So my simulation is say incompressible. Based on that, I can choose a solver type. So whether I'm using simple foam, pimple foam, steady state or transient. So all of those things you can choose from here. Then you go ahead with the submission of your abstract. So once you submit your abstract, you will get an email saying that you have submitted your abstract. Once it is approved, you will again get an email saying that your abstract has been approved. Now you can go ahead with your file submission. Okay, so this is again at a later period. For now, you have to first understand what exactly is OpenFOAM, how to run a case in it. But once you're familiar with it, and later on, if you plan on submitting something, you can, this is the procedure. In case you don't remember it, this video or this particular session will be recorded and it will be shared on YouTube, so you can refer to this as well. Okay, so I think now Payal ma'am wanted to speak about the site itself. Yeah, so Payal ma'am, are you there? Hello.
Yes, just give me some time.
In the meanwhile, yeah. So in the meantime, as Payal ma'am also shared about lab migration. So this is for faculties majorly. So lab migration, if you have a pre-existing case that is already done, or a practical that is already done in commercial software, and you want to migrate it to OpenFOAM, so the FOSSEE team helps you do that. So over here you can see the completed lab migrations as well. So this was done by Professor Dheeraj Garg from Shivanagara University. So again, you can see the problem statement. You can also see the results for each of those cases. So these are the experiments that were proposed by him, and the solution, you can view the solution over here. So the solution is this one. You can also download the entire, it's similar to the case files that you've seen for case studies and research migration. You will have a report, and then you will have the main file itself. And similarly, if you want to propose a problem, you can go to proposal. You can go to lab migration proposal, and then you can fill in this form. And in case, in case you want to know which lab migrations or which case studies also are in progress, you can see that as well. So if I click on case studies in progress, it will show all of these, so that if in case you're planning to do something similar, you can always check this out, whether already someone is doing that or not. If in case someone is doing that, then you can maybe change a few parameters, and that way it will be your own case and not a duplication. Okay, so this was it about all the things on OpenFOAM, how to get started with OpenFOAM, and the website itself.
Yeah, so Paris has already covered most of the important points about the website. I just want to talk about how can we start learning and what resources we have. And after this session, it is very, very important that all the coordinators should fill up the feedback form along with the attendance sheet that you have collected from the students, because we would need the proof of attendance of the students. I think most of you have taken geotagged photographs of the students who are attending from their institutes. So these two things we would need from you. So looking forward to your cooperation, and let me just now show you our website. So this, just a second, this is our main website, FOSSEE.in. Okay, let me just share my screen first. Okay, now it is visible, right? Okay, so this is our
Yes,
this is our main website, FOSSEE.in. Okay, and once you click on any of the icons, you will be taken to the respective FOSS. So now I'm clicking on OpenFOAM, and it is taking me to cfd.fossee.in. You can see many tabs over here. So if you're interested to know our team members, you can click over here. And this is a very important tab, services. I was talking about the course that we have recently launched, and we already have offered this to VIT Vellore, and we will be offering this to the students of IARE this year, and probably Sastra and VIT Chennai. So all of you are invited to connect to us if you want to, if you are interested to, take the opportunity of launching this course for your students as a value-added course, or it can also be incorporated in your regular course curriculum. So for all the faculty members, for all the HODs, for all the TPOs who have joined today, I would request you to please fill up this form. You can see the course, all the materials over here. I mean the forms over here. Just a second. This is the form. Okay, here you can find the form which you can fill up to apply for a course for your institutions. Okay, and these are the services that we provide to anybody who comes to us. This is for the OpenFOAM learning program that I was just mentioning. Generally, we take the students from the batch, whoever applies for the internship and fellowship programs. But apart from that, also we can screen the students who are interested, and we can shortlist some of them who can join. But here also we have a limited bandwidth because we have only 5 team members in the CFD team of FOSSEE. Yeah, today you have met Evan and Paris. We have Manjil Sitola, we have Nikhil Chidnavis, and we also have Pranay Pandey. So all the 5 people, they are the only ones in the team members. So they look after the interns and fellows, and they actually mentor them and give them the pointers to take their work forward, and they actually groom all the students who join as interns and fellows. So along with that, we simultaneously also do this learning program thing. So we don't have the capacity to take say 50 or 100 students. We have a limited capacity. Say we can take a group of 10-12 people and mentor them. So you will have to learn OpenFOAM at first. You have to gain that expertise and take yourself in that level so that you can apply to the OpenFOAM learning program, and our team members can handhold you. And this we do twice a year. The OpenFOAM learning program is run twice a year. This is the first batch we announce around January. So we expect that the people, the students who are interested to apply for the internship, they apply, and then we scrutinize the students from them. So towards the beginning of the year, the first half of the year, we have one program, and for the second half of the year, we have another OpenFOAM learning program. So this year we will announce the internship in the month of August, and whoever is capable of taking the learning from us, or whoever we think that they have the capacity and the potential to learn and excel, we are there to help them. And it actually happened with a lot of students. Say in the past 2 years, there are 3-4 students who couldn't who have attempted and couldn't get through the internships and fellowships, and they have joined the learning program, and gradually they have come up to a level that one student actually topped the fellowship after this grooming program. And so there are 3-4 instances where people actually stay with us, get trained by our team, and they develop themselves. So this is about the OpenFOAM learning program. We keep on announcing about our workshops and FDPs, so please keep checking the events tab of cfd.fossee.in. So our latest event was this one, so it is updated over here. We have a tab called resources, and here we have something called the spoken tutorials on OpenFOAM. So spoken tutorials are nothing but they are like your tutors. So this will have a voiceover and a screen, and then you will have to open it in a separate window, and then simultaneously side by side you will have to open another terminal in which you can replicate all the steps that the spoken tutorial, the tutor of the spoken tutorials is showing. So it can show you a command, it can take you to another website, and whatever the spoken tutorial is teaching you, you will have to just replicate by yourself, and you can learn OpenFOAM from the basics at your own pace at any time which is available for you after your academics, and this you can do it from anywhere, from your institutes, from your hostel or home. So we also have this instruction sheet for the faculty coordinators and for the students who have filled up the form late for this event. We actually conducted a live support session for installation of OpenFOAM. Many of you might have missed it. So for you, I would suggest that please download this installation sheet and refer to this instruction sheet, and you will be you can follow, because these steps are very much easy. In case you have any problem, we are always there over the email to help you. I have just showed our email ID, which is contact-cfd@fossee.in. So you can get in touch with us. We will be happy to help you with the installation process. So you can start learning OpenFOAM from the basics and gradually move on to the intermediate level. We have 13 tutorials over here, and we will also provide you some more links so that you can get to refer some more available references to learn and to excel in OpenFOAM. So after this program, we will be communicating through you through emails, wherein we will float the feedback form. We will also ask for the proof of attendance, and also I will give you some more references to learn OpenFOAM. So this was the resources part. Okay, for the and because there are many faculty members today who have joined, so this is the list of the publications that the faculty members do along with the students whom they train. Okay, so you can see one's name over here. Professor Tushar Chaurishi was his mentor, and you can see a lot of publications, and we actually have 4 or 5 more publications, but we are yet to receive this DOI for the papers, so we can't upload it now. So how these publications happen is, so the students actually work with the faculty members for say 2 or 3 months, 2 months in case of summer and 3 months in case of the internships, semester long internships. But this time is very much short for anybody to reach to a certain level which is needed to publish a paper, even for a conference proceeding. So what they do is, if the faculty members find that they are promising and they are trainable and they have then they can sustain with the training program, so they actually keep on working for the next say 6 months or 1 year, and then they publish these papers. So this takes time. So whoever is academic minded, and if you are into your research PhD, please consider publishing a paper, apply with us, stay connected with us, and all our faculty partners are very much enthusiastic about training. So our team is led by Professor Chandan Bose. He is a faculty member at the University of Birmingham, and he is also a visiting faculty at IIT Bombay. Professor Manaswita is there. Professor Janani Sri Muralidharan is also one of our patrons. So all of them, all these faculty members whom you can see on the screen, they are very much enthusiastic about teaching and learning the students. And to become a faculty partner, the first step is you start guiding any one of the students of your institutes. Okay, and gradually, if you have that keen interest to work with FOSS, to enhance the skill set of the students, you are welcome to join our team. So these are all the faculty partners who help us to take this project forward. And we also have the advisory board members who they also train the interns and fellows. I just mentioned it towards the beginning of this session. And both the team members, they collaborate with each other, and they also get benefit in their R&D work. For the corporate people, they get benefited in their R&D work because they have a lot of people to consult. And for the academia also, it is very good for them because they are exposed to some of the very interesting projects in the corporate world, in the industry world. Okay, and at last, let me show you our contact ID. This is our contact ID, contact-cfd.fossee.in. Okay, and so we are here. Then, if I have missed something, I can include it in the email that will be communicated after this session. Okay, so now we are open for questions from you. If you have audio problems, you can also use the chat box to ask your questions. But please don't feel that my question will be silly or should I ask it. No, we are very generous, open and friendly people over here. And I think I have missed one point, how we select the interns, right, Evan? Did you mention it?
No, ma'am, not yet.
That point I missed. So generally the selection process is very simple because we float a screening task, and the selection of the interns and fellows are based on the screening task itself. We don't look at your mark sheet, we don't look at how you perform in your institutes, because our PI Professor Prabhu and our Professor Kannan, who was leading this project, all of them believe that there are some potential in the students that the academic institutes might not be able to show up. So we believe that we should give the opportunity to each and every one. So we have this selection process, which is very simple. So it is one screening task that we float for everybody to attempt. If you get through, there will be 1 or 2 rounds of interview, and then if you are selected, you can be in a FOSSEE intern or a FOSSEE fellow. Okay, so this is the process of selection. Can you explain about FOAM application? Okay, I think for all these technical questions, I would request you to please get in touch through email. Here, if you have any general questions, you are welcome. Chat box kholu kya? Recording mein aayega.
Yeah, so Adarsh is asking that he's passed out recently. So can you apply for the... Okay, so Ashish, Adarsh, are you planning to apply for the internship? See, internships are open to anyone. So whether you are a student, whether you are a working professional, or whether you are just an individual who just is planning to learn OpenFOAM and planning to do some research, it's open to anyone. As long as you can clear the screening task and the interview, you can apply. Okay.
Yeah, so semester-long interns are fully online, and summer fellowship is in a hybrid mode. You can choose to apply in an online mode, or you can come to IIT Bombay campus during the tenure of the fellowship.
Yeah, and there was one question by Rahul. Yeah, so Rahul, regarding nuclear core simulations. So again, It's mostly multi-phase, and it depends on what you're planning to do. Like if you are just saying nuclear core design, so if you're planning to do something like a nuclear reactor design, then you can do that in OpenFOAM. There are people who've already done that as well. You can check the repository. Along with that, you can also couple a specific, like there is something known as PETICI. So you can couple that with OpenFOAM as well to solve very specific problems that are there in nuclear or in the nuclear industry that people are facing. That is regarding boiling and proper multi-phase simulation. So those can be done as well.
No, there are no eligibility criteria for the fellowship or the internship. The only thing is you should have a good knowledge of CFD, and you should learn OpenFOAM and then apply. I just mentioned that the semester long internship is fully online, and the summer fellowship is offered in a hybrid mode. You have the option of joining online and also coming here at IIT Bombay.
Akula, you just mentioned multi-phase evaporation. So what do you mean by that?
Simulation on evaporation system in refrigeration, like refrigerant.
Yeah, so if you're planning to do something like that, that can be done in OpenFOAM. So that will come again under multi-phase. That will be on your phase change. So from liquid to vapor, all
Yes,
that
sir.
can be done. Yes. Again, there will be one particular publication that is being done by one of the summer fellows right now. That is why it has been published. So he's working on something similar to that. So it's mostly related to your condensation and vaporization of liquid. So you can check that.
Yes.
So the semester long internship is for 3 months, and summer fellowship is for 2 months. Job opportunities. So Evan or Paris, you want to answer this question?
Actually, like learning OpenFOAM is a added advantage I learned back in my final year. So if you understand CFD through and through, then your chances of getting placed inside a core CFD companies increases by a mile. Here at IIT Bombay also, I know some people as they had an idea related to OpenFOAM. They got very good placements inside Mercedes or Kirloskar oil engine. So learning OpenFOAM not only opens your gateway towards CFD companies, but you can also go towards code development route as well. Which companies? Uh, Again, Mr. Shriram, it depends. If you're doing your BTech, the roles are usually around 6 to 8 LPA. But for masters and PhDs, the sky is the limit.
Actually, I would like to tell this to everybody that this job thing is out of the scope of
Uh,
FOSSEE. FOSSEE is here for training you to help you to uplift your skill level. And for jobs and all, I think from your personal level, you should inquire in your institutes or wherever you are now. Because FOSSEE at FOSSEE we actually help you to increase your employment potential, but we cannot help you to directly link to the employers or like that.
Is it according to the interest? So, Mr. Shiffin, so if you are, let us say, selected for an internship or fellowship, so you are given a list of problem statements that are floated by the professor. Depending on your ranking in
अभी ख़त्म
the
करते हैं हम
screening
हाँ
task and
तो
interviews, you are marked, and depending on the preference of what you want to work, you are matched. Once that is done, you can start the internship.
So Abhirup, the repository is free for everybody's access. You don't need to even log in to refer to the repository. I just showed you the link. You go to cfd.fossee.in, and there is a case study project, completed case study project, and you will find the repository over there. Similar thing for the research migration project. It is application for internship. Yes, it is open. Yeah, it is time bound program. So very soon we will announce the autumn semester long internship in the month of August. So the registration will be open for say 1 month, and then we will within that month we will float the screening task, and the selection process will start thereafter. Internship is not based on any opening. We float the problem for everybody. We get applications from all over India, even abroad, and we get around 300 to 400 applications every year for every internship and fellowship. And from that we choose say 13-14 people. Okay. So if we don't have any more questions at present to ask our team, we will yes, okay. So Giri Shankar. Mr.
Ma'am, am I audible, ma'am?
Yes, yes.
Ma'am, if I have selected for the semester-long internship,
Yes.
once shall I apply again for the fellowship, ma'am?
Yes, you can. We will do.
Okay, ma'am. Thanks.
Okay, so it's already 6:15, and we are time to close the session. So all your other questions are welcome through email. So please write to us at contactcfd@fossee.in. I think Paris has just pasted it a while ago. Ivan has pasted it. So please respond to the feedback form, because it is very important, because then we will it will help us to get in touch with you for the future workshops that we announce, and for the future programs also. Okay, so for today, thank you so much, Shriram. Thanks a lot. So for today, let us conclude the session over here. Please be in touch, because this is the beginning of the association of you with FOSSEE. So thanks a lot, and bye bye.